Go for it.
Okay, so sir, since we know that energy is mgh, the mass is going to be the total mass, so it's going to be 2250 minus 1300 times by 40 meters.
That's cheating. Okay,
What?
but yeah, carry on.
So how's it cheating?
Why is that the total mass?
Sir, because it's like there's like a mass of the counterweight, so the mass is less now.
Yeah, I know what you mean. It's physically incorrect to say the mass cancelled out. Okay, you have to look at it in terms of the forces cancel out, so mg cancels out. But this works, so no problem. Carry on.
Okay, and then so do we do times 40 and then times 9.81?
Good. So
And then all of that over t, which is 30 seconds.
Good. What you technically did is you did work done over time, where the work done is the force times distance, and the force is the force of gravity, which is weight, which is mg. And that's, by the way, where mgh comes from. So good. What did you get as the final answer? 12,000?
So wait, let me do it.
Wait, so I don't get it. Why are you subtracting the two weights?
All right. It will make sense if I do it this way instead. So let's say power is work done over time. Work done is force times distance, right? This force is the force acting, the total force acting on the lift. What's the total force acting on the lift? Well, you got mg downwards and mg of this lift, right? The weight of this lift upwards. Does that make sense? So the downward force is from this. So it's 2250 times by g, which is 9.81. And this is minus this force here, the weight of this force, which is 1300 times by g. So this is the total force acting on the lift, because you got the mg from the lift, and then you also have the mg, or the weight of the counterweight, right? So the counterweight's applying its own force, which is equal to its mg, which is 1300 times by 9.8. So this is the total force required to lift the lift. Does that make sense?
Yeah.
So that's why you had to minus. So it's better
Sir,
to...
so then sorry, continue.
Yeah, so it's better to think about it in terms of forces usually than mgh. Just because if there was an explain question next, you can't really explain it if you said you minus the mass, or you could explain in terms of the resultant force. Yes, Saleh?
And then with that answered, all divided by 30, you get 12,426 watts, which is around 12.4 kilowatts, which is around 12 kilowatts.
I'm going to say 12.4 kilowatts, if you want to keep it in kilowatts, or 1.24 times 10 to the 4 watts. The reason I'm using 3 significant figures is because every value I used was at least 3 significant figures. This was 3, this was 3, this was 4, this was 4. So I had to technically give it to 3 significant figures, or I would have dropped a mark. So yeah, let's carry on. The electric motor dissipates energy to the surroundings at a rate of 3,600 watts. Determine the efficiency. 100% you would have all told me you start by writing efficiency is useful energy over, or useful power, because we're talking about power here. Useful power over total power. Okay, I'll give you 1 minute, and then Isa's going to tell us his answer.
Sir,
Yes.
is it 1.24 times 10 to the power 4 over 1.24 times 10 to the power 4 plus 3,600.
Excellent. That is spot on. The reason that's the case is because what is the useful energy? You have to look at the system. Well, the useful part is the work done in the lift. It's moving the lift up. That's the useful aspect. So the useful is what we worked out, which is 12,400. And I know it wasted 3,600. So 12,400 was the useful. Useful plus wasted is total. So plus 3,600. What do you get, Isa?
77.5%.
Again, I'm going to put three significant figures as you did. So 77.5%. Excellent. You technically times by 100. So I'll put that on your working out. Good. So let's move on. A tile. What is that? A transverse. A Tyrone transverse is a technique for crossing a deep valley. The photograph shows a climber crossing a river using this technique. The climber moves along a rope. You're going to notice all these physics questions, all this information is most of the time useless. And it's just, oh, what's the equation? What's the this? So don't worry if you're like me and you don't know what's going on yet. The climber moves along a rope, suspended from the bank. You need to know what this word suspended means. It's also used in mechanics. What can you deduce from the word suspended? Something suspended, was it clear about the forces?
They're balanced.
Good, there is no resultant force. This is the same thing as it's moving at constant speed or it's stationary. It's just another word for that. So I'm gonna give it annotation. No resultant force. F resultant, okay. The free body force diagram for the climber is shown below. The weight of the climber is 650 newtons. Show that the tension is this. I'll give you 2-3 minutes. And then we'll get Muhammad to walk us through what his thoughts are. You don't actually need the information in the box. I'm just going to zoom in here.
Sorry, I think I did it.
So do you use the vertical component?
Yes, you do.
So can I say that it would be 650 newtons is equal to 2 times t cos 76?
Excellent, beautiful. And I'll just add some commentary. Every single question where they show you vectors and angles, you know you're resolving into horizontal and vertical components. That's never not been the case. So already, like, it's a good idea to just resolve this annoying vector. This is 76. This will be 14. And this is t, right? The hypotenuse is t. So this is t sine 14. Of course, there's also a t sine 14 here because it's basically mirrored. And then, as Muhammad said, very well done. He said, let's consider the vertical components because it is, remember, it's suspended, so there's no resultant force, meaning there's no resultant force horizontally or vertically. Well, the horizontal components cancel out. They're just both t cosine 14. You got t cosine 14 on the left and t cosine 14 on the right. That's useless. It doesn't allow me to work out what t is because it just cancels each other out. But the vertical components, we do have a value to help us. We call this a reference. But this reference is very useful. Actually, that reminds me of the question we did in, let me show you in the mock. So always good to make these links. There was a question. Where was it? This one. So there was this question where it says, how can you work out the mass, right? And then what you have to do is, oh, I'm given a reference, which is the mg, or work out the tension. Sorry, well, I know the reference, which is there's a force down, which I know what it is. It's just the mass times 9.81. So what I can say is, because it's in equilibrium, the vertical forces balance out. So this is theta. So this is going to be T sine theta. So what I can say is T sine theta is equal to mg. This sort of question, if it comes up and you're able to notice the skill set, honestly, it's 3 marks, like easy peasy marks. So let's do that. So the forces vertically have to balance. So 650 is the forces down, and that's equal to the forces up, which is 2 times T sine 14. Rearrange. So T is equal to 650 over 2 sine 14. What did you get, Hamad?
I go 1.343408 times 10 to the power of 3.
Times 10 to the power of 3 newtons, which is around 1.3. If you round to 2 significant figures, excellent.
Thank you.
The rope has an unstretched length of 120 meters. Determine the strain in the rope while it is supporting the weight of the climber. You may ignore the weight of the rope. So this one will be for Faizan when he's ready.
Sir.
Hmm?
So when I get the answer and then so how do I so for this question it's 3 sig fig, right? Because everything's rounded to 3 sig fig, or
Yeah, I would use 3 sig figs.
3 sig fig. Okay.
You might be tempted to say the angle is 2 significant figures. This is like a weird hidden rule where, 2 sig figs of an angle is equivalent to like 3 sig figs of something. I don't know this, but 3 sig figs or 2 will both score you the marks in this question. So what did you do?
Me?
Faizan.
Faizan.
So I know you need to find the extension, but I'm just a bit confused on how you're supposed
Good. So
to
stress
how you do that.
extension over the original length, and you know the original length is 120. So this is the absolute minimum you should be writing in your exam to score 1 out of 3 marks. So originally the rope was like this, and that's 120. Now the rope is like this. How can I work out this new length? Because if I could do the new length minus the old length, that's the extension. What do you reckon, Fizan?
So would you use
Mhm.
SOHCAHTOA?
Of course, right? We don't give you these diagrams for no reason. So if I were to transfer this triangle, it's basically a right angle triangle, angle 76. Well, this is going to be 60 because it's 120 divided by 2. We're trying to work out what this x is. So I'll let you continue from there, Fazan.
Okay, so what you do is 60 is your opposite, your x is hypotenuse, and the one at the bottom is adjacent. So you use SOHCAHTOA, so you have to use sine. So you do 60 over sine 76. And you get the extension as you get 61, but so the extension is going to be 1.83 or whatever. So you do 61.83681.776 minus 60, and the extension is 1. Wait.
So what was
Okay,
60
that's
over
like
sine?
61.836.
61.83. Is that the new length or is that half of the new length?
That's a new length, but that's not the extension you need. So you have to subtract that by 60 to get the extension.
Yeah, that will actually work. Or you could, I was just thinking, well, the new length is this times by 2, and then you do
I
that.
was gonna do that, then times it by 2.
Yeah.
Because the total extension is 3.6736.
Okay, so the extension is 3.736. You were telling me extension is 3.736. So we're going to do strain is 3.736 over 120. What do you get?
So I got 0.0306.
0.306. So 0.031 to two significant figures, or you wanted 3, so 0.0306 also fine. Excellent. No unit because it's strain. The rope has a cross-sectional area given in meters
Sir?
squared. Yes.
So I have a question. So how are you supposed to know you're supposed to use SOHCAHTOA there?
Because you're trying to work out the new length, right? Because you want the extension. And this is the new length. So if I could work out the size of one, I could work out the size of the other. I'm given an angle, I'm given a side, so SOHCAHTOA. That's, I guess, the only way. But I mean, every time they give you sides and angles, either you're resolving or you're doing SOHCAHTOA, like trigonometry. Either a squared plus b squared c squared, or sine or cosine or tan, or you're doing the horizontal vertical components. Otherwise, they won't give you this sort of diagram, would they? Does that make sense?
Yeah, okay, thank you, sir.
No problem. So determine the Young's modulus of the rope material. Saleh, that's for you when you're ready.
Sir, did you say me?
Yeah.
Okay. Okay, so I think I know what to do. I'm just gonna like go do it as I go.
Yeah, go for it.
Okay, so sir, I know that Young's modulus is stress over strain. We have the strain, which is 0.0306, And we know that stress is F over A. And we know that the force is 650 newtons downwards. And they already give us the area. So we do 650 over 3.14 times 10 to the power of -4. And then we do that over 0.0306.
Wait. What did you use as the force?
650 newtons.
No. The force in stress over strain is the tension on the entire string, rather than the force in one particular part. So actually,
So how do you do it? How do you get the F
that's,
there?
that's what we did in part A.
So we'd use 1.3 times 10 to the power of 3.
Yeah, so 1.343.
Yeah.
So 1. So I guess that's a skill set on its own. Just know that the force in stress over stress and force over area for stress is the tension on the string
Okay.
over the area.
And then
Which
we do that, which is that it gives it to us. And then whatever that value is, I'll do it right now on the calculator.
good. So lambda modulus is stress, which is 0.0306 over the strain, which is 1.343 times
So
10 to
we
the
get for the stress, it's 4277070.064.
Well, yeah, whatever you get. I don't
And
disagree.
then that'll be over what was the strain again? 0.0306.
Yeah, so strain divided by that number.
So I get 139773531. So like that's gonna be 1.4 times 10 to the power of something.
Yeah, good. 1.4 times 10 to the 8. 1.4 times 10 to the 8. They used two significant figures. I'm a little bit curious why they did. No, sorry, they didn't. They used 1.38. Yeah, sorry. Yeah, okay, that makes sense. It should be three significant figures because that's what everything was given to.
So if I got 1.39, would that be wrong?
Did you round anything?
No, I mean I just used the value that I got, and then
Did you round the stress?
no sir, the stress I just pressed the answer on the calculator over. I got 1.39, not 1.38.
And the
So maybe
units
I
of
rounded
stress,
it
yeah.
from before.
If
I
you
don't know.
didn't round and you got 1.39, then that would be accepted. So don't worry about that.
Okay.
Oh my God, another lift. A student of weight 600 newtons is standing on weighing scales in a lift. The scales are calibrated to give readings in newtons. And by the way, I can see a star here. It's a 6-mark question. And we want some like nice, clear answers. Let's see, who can get 6 out of 6? I'll be really impressed. I'll take multiple answers for this. So yeah, he weighs 600 newtons. He stands on the lift. And the lift gives the reading in newtons, i.e. it gives the force. It gives his weight. The lift moves upwards at constant velocity. Okay, so initially it's moving up, the velocity is up, and is decelerating to rest. So although the velocity is up, it's accelerating downwards until the velocity is 0. As the lift moves, also I see a constant velocity here. That should ring a bell in your answer. As the lift moves, the student looks at the readings on the scale. Explain the readings on the scale. 6 marks. I'm gonna give you all 4 minutes. I'll be back in 4 minutes too. Default has changed to. Can you guys hear me? Yeah, you can. Okay, so yeah, I'll give you 4 minutes. Do this and let's see who could get like 5 or 6 marks. I'd be really impressed because if you could get the 5 or 6 marks, it means you've understood a certain topic really, really well. Anyone finished?
Sir, to be honest, I have a bit of it down, but like I don't think it's 5 or 6 marks anywhere near it.
Go on, give me your full answer now. I'll tell you. the maths.
Okay, sir. So initially, as the lift moves upwards, it's moving at constant velocity, which means there's no resultant force. So the weight that the student exerts on the scale and the lift is equal to the weight that is equal to the reaction force exerted from the lift onto the person, which gives the reading of the scale. So it's constant in the beginning, so the reading stays the same. But then when it starts to decelerate, there's a resultant force downwards. And then from there, I'm not sure.
No, lots of really good things were said.
Sir,
Yes, Faizan.
so I'm confused. Like, I think I know the rest of the answer, but the thing is, like, so why do you have to consider reaction force as the reading on the scale? That's what I'm like a bit curious about.
We'll talk about that now. So I would have started just like you started and talk about the constant velocity. So initially, the lift is moving at constant velocity. So there is no resultant force. Make a Newton's first law reference, if you please. It doesn't really say explain in terms of Newton's laws, so that reference wasn't needed. So because there are no resultant forces, there's no external resultant force acting on the human, meaning the human exerts a force on the weighing scale, which is equal to his weight. Because that's generally what happens normally. If you stand, then you're going to exert a force on the floor. Therefore, and this is due to Newton's third law, the scale exerts the same force on the human. And this force that exerts is the reading on the scale, because that's just how a scale works. So if you get on a scale, do you guys know how a force meter works? Have you seen a force meter before? Or a picture?
Yeah, it's like the thing with a spring, right? And then you
Yeah.
attach.
Excellent. A thing with a, there you go. A thing with a spring. So the more force you apply, the more reading it gives you. This is literally how a scale works, but instead of extension, it uses compression. But it works in the same way. It has springs, it has 4 springs on each. It's not the question, the question. It has like 4 springs on each end, and depending how much the springs compress, it's going to give you a different reading. So well, what force is he exerting on the lift? That's the reading that the scale is going to give you. Does that make sense? Faizan?
So can you repeat it again, please? I'm confused a little.
So I'm saying the way the scale works is basically a force meter. In a force meter, whatever force you apply, that's the reading it gives you. Okay? This is the exact same thing. Whatever force you apply on this scale, that's the reading it's going to give you.
Yeah, but so wouldn't that mean like, so
So
like,
what force is
look,
he
for
applying
example,
on this scale? Yeah.
it's gonna be weight, right?
Yeah.
So why is reaction force and not weight?
Good. So right now, he's applying a force on the scale. The scale is applying a force back on him. When the lift's accelerating, what are the new forces acting on the human? So let's say the lift's accelerating now. Before we just had mg acting on the human, right? and obviously the reaction force from the lift. But now that if the lift's accelerating, there's going to be a force upwards, correct? There's going to be a force pushing him upwards. Or if it's in this case is decelerating. So if it's decelerating, what's happening? There's a force downwards acting on the human, correct? So far, so good. So now there's mg downwards and also the force from the deceleration pushing him down because the lift's decelerating. Does that make sense?
So I'm still a bit confused why it's reaction force.
Yeah,
and not
we
just-
haven't reached that yet. We haven't reached that yet. Just does it make sense how right now there's his mg is pushing him down and there's also the force, the lift is pushing him down because it's decelerating. Right. Well, now the total force, okay, the total force acting on the lift is his mg and F. So if you just said the, what's it called? The force acting on the scale is just mg, how are you going to explain that once it decelerates, there's also plus F over here? However, the resultant force or the reaction force, sorry, is always whatever is acting on the lift, whether it's his mg or his mg plus something else, or whether his mg plus his phone's mg and someone else pushing him down. So this reaction force is just basically equal to the total force acting on the lift. That's why we refer to it as a reaction force. Because here's your lift, here's your scale. Here's your scale. The total force acting on the scale is what gives you the reading. And the total force which acts on the scale is the total force the scale is going to act on the human or whatever's standing on it, right? So let's repeat that one last time. The total force acting on the scale gives you the reading, and the total force acting on the scale is going to apply the same force backwards. That's why we refer to it as the reaction force. Because if the force pushing down increases, because there's mg plus the lift or plus something else, then the reaction force is going to increase. If it decreases, the reaction force decreases. So it just makes more sense to talk about it in terms of the reaction force. But technically speaking, the reading of the scale is the force applied on the scale. Technically speaking, the scale gives you, so I'll explain this one last time. The reading on the scale is the force you exert on the scale. And the force you exert on the scale is the force the scale will exert on you. That's why we talk about it in terms of the reaction force. But no, you could have said the reading on the scale is the total force exerted on the scale. That's also correct. It just makes more sense to refer to it as the reaction force. Does that make sense? No?
So in the exam, if they ask a question relating to like a scale or a force meter or anything, you'd like refer to it as a reaction force, right?
Yeah, the reading on the scale will be the reaction force. Yes. Okay, so let's rub all of this out. Go back to the answer. Because there are no resultant forces, the human exerts a force on the weighing scale which is equal to his weight. Therefore, due to Newton's third law, the scale exerts the same force on the human. The reading on the scale is equivalent to the total force exerted on the scale. And we just said the total force exerted on the scale is the same as the reaction force. Because whatever you exert on the scale exerts on you. Yes, Isa.
So I think I know what to say now, like for the last part to get all the marks.
Okay, just let me just finish this. The reading on the scale is equal to total force exerted on scale. This is the same as the reaction force. The scale exerts, okay, on the human or whatever is on it. Okay, carry on this answer for us.
Okay, so then when it starts to decelerate, there's the resultant force upwards, right? Sorry, resultant force downwards.
There is now a resultant force downwards. Good. Because we said the acceleration is down. Mhm.
Yeah. So that means that the force acting down the weight must be greater than the reaction force acting upwards. So the reading will decrease slightly. and that's it.
Good. The only way you could have a resultant force downwards is if the weight of the human is larger than the reaction force. Right? Because now your forces down are larger than your forces up. Let's consider the forces acting on the human once again. You got mg downwards, and you got the reaction force upwards. But we know he's accelerating. Therefore, there is a resultant force downwards. It's only possible to have a resultant force downwards if this is larger than this, correct? Right? So far, so good. However, does mg ever change? Does his weight ever change? No, his weight is always his mass times 9.81. So this downward force acting on the human never ever changes. So how is it possible to have a resultant force downwards? That means the reaction force must have decreased. Does that make sense? I'll try to explain it one last time. You guys need to talk. Tell me yes, no, maybe. So let's just consider an object where the force acting on it is downwards is its weight, and the force acting on it upwards is the reaction force. At the start, okay, initially, the reaction force is equal to your weight, meaning initially, it's moving at constant velocity, or the acceleration is zero, or there's no resultant force. We know that. Okay, now we're saying there is a resultant force, meaning this is only possible if mg minus r has to now be greater than zero. mg has to be greater than r for you to have a resultant force downwards. But mg could never change. The weight of the human could never ever change. So how is it possible to have a resultant force downwards? That must mean your reaction force would have had to have decreased. So you're going to write this like so. As the lift decelerates, there is now a resultant force downwards. Therefore, weight is now larger than the reaction force. The weight doesn't change, meaning the reaction force must have decreased. Since the reaction force is the reading on the scale, that must mean the reading on the scale decreases until it says until he's at rest. So until he is at rest, the resultant force is now zero again, meaning weight equals reaction force. So the reading on the scale would be his weight. And because it's given us the value 600 newtons, which is 600 newtons. We'll write that at the start as well. So because they're on, which is equal to his weight, brackets 650 newtons. Wait, what happened? Yeah, there you go. Any questions? Shall I explain it one last time, like from start to end, or shall we move on?
So I think it's fine if we move on.
No, let's move on. Just, I guess, key thing to know is for any balance or scale, the reading on the scale is equivalent to the reaction force. Why? Because the reaction force it exerts on the object is the same as the object exerts on the reading. So technically, the reading on the scale is the total force acting on it, just Newton's third law. A hollow brass cylinder with closed ends is floating on the surface of water. The cylinder has length 4 centimeters and an external diameter of 2.1 centimeters as shown. 63% of the volume of the cylinder is submerged. The cylinder contains negligible weight of air. Explain why the brass cylinder floats. Muhammad.
So for 1 mark, I could say that the upthrust is equal to the amount of water displaced by the cylinder. I'm not sure what to say for the second one. So I can't hear you.
Oh, sorry, I was muted. I was talking. Okay, I was saying, why does it float? What does it mean if something floats? In terms of resultant force.
There's no resultant force.
Good. There is no resultant force acting on the cylinder as a weight of the cylinder equal to outforce. Good. Whoever, yes, Faizan.
So if it's floating, wouldn't it mean that there's a resultant force upwards?
No, if there's a resultant force upwards, it will rise. Slightly different terminology. Rise is up, sink is down, float is it just stays whatever it is.
Oh yeah,
Uh,
okay, my fault.
Yeah, if upthrust is greater, that means there's a resultant force upwards. There's a resultant force upwards, gonna, accelerate upwards. So yeah, this question. Whether it's floating or what's it called, suspended as we did previously, or constant velocity, or stationary, or at rest, all these words mean one thing. There is no resultant force. So the upward forces are the downward forces, or left forces or right forces, or both. Okay, the density of water is 1,000. Show that the mass of the cylinder is 0.009 kilograms. We will get Asa to do this when he's ready.
Sir,
Yes.
sir, how are we supposed to get? How do we get the volume of a cylinder? Do they give it to us in the exam?
No, you have to memorize the equation for volume of the cylinder, which is pi r squared multiplied by the length.
Ah, okay.
Spare cylinder, cube slash cuboid are the volumes Newtonal. Any progress?
So I know how to do it. I'm just not getting the right answer. I don't know.
Okay, tell me what you did.
Okay, so so because we know that the up thrust equals the weight, right? So what I did was I worked out the up thrust first because they gave us a density of water. So it was 1.
Good. I want to
sent
stop
it-
there for a bit, because just so everyone understands. So obviously the natural thing to do in a question like this is it wants the mass. So mass is density times volume. However, it's not giving me the density. And even if it's giving me the density, I cannot use that density because it's hollow, right? When you do mass is density times volume, you expect the entire volume to be filled with that material. So this approach is not going to work. We cannot think about this. So instead, we had to realize, as you said, up thrust is equal to weight. So if we know what the up thrust is, we know what the weight is. And if we know what the weight is, we know what the mass is, because mass is the weight over 9.81. Okay, sorry, carry on.
Okay, so first I worked out the volume by doing pi squared multiplied by the length. So 2 times 2, 4 pi multiplied by 2.1. Yeah, and that gave me. So is that right? It's for the volume.
Yeah, so the volume is pi r squared. The radius is 1.05 because the diameter is 2.1. But I had to divide by 100 because it's given
So,
centimeters.
so why is 2.1 the diameter?
2.1 is the diameter because this is a cylinder, okay? And it's saying that this is 2.1.
It looks like, oh.
Yeah, I know it looks like that because you're looking at it from this angle. Forget about what it looks like. It's labeled a cylinder.
No, sir, because I thought it was like I thought 4 was the diameter. Like it's like where I can annotate, right? I thought it was like something like this.
To be fair, they've made sure you cannot think that because they said an external diameter of 2.1. So yeah, I guess your thought process is correct, but you know they've even shut that one down.
That's probably what I did wrong. Okay.
Yeah, so pi times the radius, which is 1.05 over 100 to go from centimeters to meters, squared multiplied by the length, which is 4 over 100, because again, from centimeters to meters. Do this, Isa, and tell us what is the volume.
So I got so I'm getting 441 over 100 pi.
Okay, which is?
So I say we just leave it like that because it's more accurate. If you want a decimal, 13.854.
13.854.
4. Put another 4, yeah. So.
Yeah, but what? 13.8554 bananas?
Volume, centimeters cube.
Oh, okay. I want a meters cube, please.
Wait.
Let's keep it in standard form as well. So 1.3. One, two, three, 4, 5, 6.
3.464 times 10 to the minus 6.
Oh, times 10 to the minus 5 because I kept it in standard form. I did 1.3. Good. So yeah, a meters cubed. That's the volume.
So why 1.3? Where's 1.3 come from?
You said 13.
I said 3.464.
3.64. That's not what I got when I put in my calculator. Let me, who wants to confirm? Guys, who else put this in the calculator? Let me check the marks on this. Okay, they said the volume of cylinder is 1.39
Oh,
times
it's-
10 to
yeah. Yeah. So then you can work out the upthrust by using the volume multiplied by the density multiplied by g.
Mhm.
So 1 times 10 to the power of 3 multiplied by 1.38 times 10 to the power of -5 times 9.81. Now what does that give me? Uh, 0.1359 as the upthrust, which also equals the weight, which is mg.
So m is equal to
So just divide by 9.81 to get the mass, which is I'm getting 0.014. Yes, so it still doesn't prove it.
interesting.
Saying show.
I understand why. Because it says 63% of the volume is submerged. When we worked out the volume, we assumed 100% was submerged. So we're gonna have to multiply this one by 0.63.
Oh, okay. So it's -6, no? 1.3854 times 10 to the -6, or does the mark scheme say -5? -5, okay.
Yeah, -5.
10 to the power 3. Oh yeah, okay, yeah. So now I'm getting 8.7 times 10 to the -4, which almost equals 9 times 10 to the -3. Oh, sorry, 8.7 times 10 to the -3, which is the same as 9 times 10 to the -3.
So this is why I got my calculator. Times 10 to -6 meters cubed. That's the volume. So I'm gonna do this 8.76 times 10 to -6 multiplied by the density 10 to 3 multiplied by 9.81. So this is my upthrust, which gives you
So you're gonna divide by 9.81 anyway. So it's really just 8.76 times 10 to the -6 times 10 to the power of 3. 8.76 times 10 to the power of -3
very well done. Kilograms. And that is
kilogram.
the answer. Fantastic. Yeah. So that's how we do this. So something even I forgot, to be fair. What we should have done is highlighted it. When we saw that 63%, the first thing we should have done is highlighted it. 63% is submerged, meaning the volume of water displaced, because remember, we literally said on this question, upthrust is the weight of fluid displaced. Weight is volume times density times G. So the volume would be 0.63 times the full volume. Good, that will give us, which is around 9 times 10 to the 3 kilograms. Sorry, I'm just so tired, so tired today. Deduce whether an identical hollow cylinder made of gold would also float. Assume that the volume of gold is the same as the volume of brass. Four marks. It's giving you the density of gold, the density of the brass. And it's trying to say, would something made of gold float? What's the condition for it to float? The condition for it to float is this upthrust, which is the density times volume times G, has to equal to the mass, which is, it's not giving us the mass, we'll just write mg. I think there's this, I can think of two ways to solve this. Have a go. You guys need the values above, so I'm going to write down, I'm going to first of all write down the volume, which is 8 point, no, we're not going to write that volume, we're going to write down the full volume. If you want to use the 63%, feel free to. But the full volume of the cylinder is 1.38544 times 10 to the minus 5 meters cubed. And what else you might need? Oh, I think that's it really. So the density of the water. Density of water is 10 to the 3. Okay. Which variable expert could solve this? Relationship expert. I'll give you 3 minutes.
Sir?
Mm-hmm.
Sir, I have to go a bit early, but will this all be on YouTube?
Can you wait like 2 minutes?
Okay, sir, I'll try my best.
Yeah, okay, I'll just explain this now quickly then, because this is not something that is easy to explain. So you need to understand, for it to float, the upthrust has to equal to the weight. The upthrust is the density of the fluid, which is just 10 to the 3. That's the density of the water. The volume is the same volume as previously, which we worked out to be 1.38544 times 10 to minus 5, multiplied by 9.81. This is your upthrust. Work it out, and you get what you get. I think we worked it out before by accident. So someone else worked that out for me while I talk about mg. Well, to work out the weight, we need the mass. It's not giving me the mass of the gold, but it's giving me the density of the gold and the density of the brass. What you need to know is mass is equal to density times volume. Therefore, because the volume is constant and doesn't change, we could deduce that mass is proportional to density, meaning if the density doubles, the mass doubles. We know the mass of the previous one. Therefore, we could work out the mass of the new one, because we know that the new density is 19.3 over 8.7 times larger than the previous density. So this is the new factor. So we're going to do 19.3 over 8.7 multiplied by the mass, which was 8.76 times 10 to minus 3. This is going to give me the mass of the gold, and then obviously times it by 9.81. So let's say that the weight, which is mg, is going to give me this. Let's say this answer is equal to A. So let's say A times 9.81. So who did upthrust? What did we get for upthrust? Anyone?
Sir, I'm getting 0.135911664.
Okay. Newtons. Okay, that's our upthrust. Okay, what about the weight of the gold cylinder? which is 19.3 over 8.7 times by 8.76 times 10 to the minus 3, then times by 9.81.
So sir, you want to do whatever is in the bracket times by 9.81.
Mm-hmm.
I'm getting 0.1906.
According to this, the weight is larger, it's going to sink. So 0.1906 is greater than 0.136. So the mg, the weight of the brass is greater than the upthrust, therefore it will sink. Just double check the mark scheme. It's not good. Correct conclusion. 1.9, 1.4. Yeah, good. So 0.19, 0.14, that's what we got. Therefore, it's going to sink. Excellent. Does that make sense, Saleh?
Yes,
Okay,
sir.
go.
So the upthrust being equal, we need the upthrust to be equal to the
mg.
weight so it doesn't sink.
Good.
Okay, thank you, sir. I have to go now. Have a nice day.
No problem. All right, the rest of you three, did this question make sense? I could go over it in more detail now.
So can you go over it, please?
No. So the first part made sense, I'm assuming. For it, we need to work out what the weight is and work out what the upthrust is and compare it. Okay? And then the upthrust is just the volume times the density of the water or the fluid. The density is 10 to the minus 3. This is the volume we worked out in the previous question. Because it's the same volume, it says assume that the volume of the gold is the same as the volume of the brass. So this is the density times the volume times by G, and that was our upthrust. And we got 0.14 newtons to 2 sig figs. So far, so good? Yes, no? Isa?
Yeah.
Faizan?
Yeah, I'm good, sir. I got it.
All right, so that's the upthrust. We worked out the upthrust. Now we need to work out the weight and then make the comparison. Because if the weight is larger, it will sink. If the weight is less, it will rise. If it's the same, it will float. So let's work out what is the weight. Well, to work out the weight, which is m times g, we need the mass. But it's not giving me the mass anywhere in the question. So now my task is, can I somehow work out the mass of gold? It's giving me the density of gold. So it might be tempting to say mass is equal to the density of the gold times by the volume of the gold. But why can I not do this? Why can't I just say, okay, mass is density times volume. I know the density. I worked out a volume. Why can't I do this? Because it's hollow. The whole thing isn't made of gold. When you say mass is density times volume, you assume this volume is full of gold. You don't assume half of it is empty, do you? Does that make sense? This volume we worked out is the volume of the entire cylinder, but the entire cylinder doesn't all have gold. Just the outside has gold. So that's why you cannot just say, oh, mass is density times volume. That's incorrect. So rather, what you can say is, oh, I know what the mass of the brass is. I know what the mass of the brass is. I don't know what the mass of the gold is, but I do know the relationship between density and mass. Density is proportional to the mass. If the mass doubles, the density doubles. If the mass halves, the density halves. If the mass increases by a factor of 2.7, the density increases by a factor of 2.7, or vice versa. So I know what happened to the density. I know that the density increased from 8.7 to 19.3. So I know that the density increased by a factor of 19.3 over 8.7. That's how much times larger the density is now. That's how much it increased, which if you put in your calculator, 2 seconds, put in your calculator, you get 2.21. So the density increased by a factor of 2.21. What does that tell you about the mass? It tells you the mass increased by a factor of 2.21. And the mass before, we worked it out. We worked out the mass of the brass. It's 8.76 times 10 to minus 3, meaning the new mass, the mass of the gold, is going to equal to the mass of the brass, which is 8.76 times 10 to the minus 3, multiplied by 2.21. So the density increased by 2.21, therefore the mass must have also increased by 2.21. This is the new mass. Okay, so now we know the mass, we could work out the weight. We just do weight is mg times 9.81. So you just times whatever you got on top by 9.81. And then apparently you would have got 0.19 newtons. So clearly the weight is larger. So we're going to say the weight is larger than the upthrust. Therefore, it sinks. Does that make sense?
Yeah, so kind of. Well, give me a second, please. We're working out.
No problem.
So how do you get the mg again? The mass?
Okay, so I didn't know the mass, but I knew that the density increased by 2.21, or the density of gold is 2.21 times larger than the density of brass, correct?
Yeah.
So if the mass of the brass is 8.76, that means the mass of the gold is 8.76 times 2.21, because density is
Okay.
proportional to the mass. If the density increased by 2.21, the mass must have also increased by a factor of 2.21.
Okay. Yeah, I understand. Thank you.
So initially, what you did is, did you work out the upthrust, the upthrust from the upthrust needed for the gold?
Yeah, upthrust is just the weight of the fluid, which
Oh,
is
the upthrust is the same, right?
yeah,
But it's the
same.
weight that changes.
It's the weight that changes.
Oh.
Because
Okay.
the upthrust only depends on the volume of the object, which is the same, and the density of the fluid, which is the same, because it's under the same fluid and has the same volume. Therefore, upthrust did not change.
So because the density and mass are directly proportional, because it's 2.21 greater, you can just multiply the mass by 2.21 to get the mass for gold.
Excellent. Yes. And this is the hardest skill set in physics. It comes
So I
up
wouldn't
like
have
once
thought that,
every
yeah.
comes up once every year or two. It always does come up, by the way, like every year or two, this skill set comes up where you have to find a variable. The variable could be a volume, it could be mass, it could be kinetic energy, it could be power, it could be force, it could be velocity, it could be anything. But then there is no equation for you to work out this variable. However, it tells you that, let's say you're trying to work out force, okay? It tells you the mass increased from 70 kilograms to 110 kilograms. So what you know is the mass is 110 over 70 times larger. And then let's say you're trying to work out force and you do acceleration is force over mass. And you're like, oh, I don't know what the mass is. I don't know what the mass is. It doesn't tell me anywhere. But what you could use this relationship. You could say, oh, if the force increased, so look, F is equal to M times A. So you could say force is proportional to mass. So what you can say, oh, if the force increased by this much, the mass must have increased by this much. Or if the mass increased by this much, the force increased by this much. So it's just trying to find a relationship from some sort of equation. It's very hard to teach and use, but it does come up every now and then. So be wary. I would say if there's a question where, like this question, where you're trying to work out mass, and I don't know how to work out mass, but then all of a sudden you're given density, then what you should be thinking about, okay, how is density related to mass, for example? Because look, this is part II. You should also know that part II always uses the answer from part I. So this is another hint that I had to somehow use the mass of the previous question. So all these bits of information do come together with enough practice. So actually, straight away, you should have known that I'm going to somehow have to use this mass. And I know that the density changed, therefore the mass would have changed. Something like that, I don't know. It's not something, it's not like a topic you teach. It's just, you know, relationships. Any other questions?
No, sir.
Okay, I'll send a video for that question you had, you and Asa, on the group chat so you can watch it.
Okay, thank you.
Okay, take care. I'll see you all on Thursday, inshallah.
Bye, sir. Thank you.
Thank you.